Since we've been taking a look at exponents and also radicals, there's a relationship between fractional or rational exponents and the radicals. And so first off, if you want to just remind yourself that if you have something like 5 to the third, that means 5 times 5 times 5 equals 125. And so if we have something like 4 to the second power, that's 4 times 4, which is equal to 16. So then the question is, well, what happens if you have like 4 to the 1/2 or 4 to the 1/3? Well, that is actually equal to the square root of 4. This is the third root of 4. If we write 4 to the 1/4 power, it's the fourth root of 4. And so now that could keep going on as 1/5, 1/6, and so on. And so why does that actually work? Well, just a little example. If you have something like x squared times x squared, this would be equal to, well, we've already done this, xx and then another xx, and so we get x to the 4th power. So what about if we have, let's do it with the numbers this time, like 9 to the 1/2 times 9 to the 1/2. Well, you can see up above that these exponents basically add together. So we have 2 of those and 2 of those. So when you have a fraction, it's going to be 9 to the 1/2 plus 1/2 power, which would be 9 to the 1, which equals 9. So 9 to the 1/2 power times itself gives you, or squared, gives you 9. And so when we call a number that does that, the square root. So we know that the square root of 9, when we square it, we get 9. So that notation for a fractional exponent really just means radical or square. Okay, let's look at that again. How about 16 to the 1/4 times 16 to the 1/4 times 16 to the 1/4 times 16 to the 1/4? Well, that's really just 16 to the 1/4 plus 1/4 plus 1/4 plus 1/4, which will equal 16 to the first power, which is 16. So when we have 16 to the 1/4, multiply it out 4 times really, this is going to be equal to the number 16. So we know that the fourth root of 16 to the 4th power is 16. So all our definitions are matching up. So we have a general rule then that says if you have any base x to the 1/n power, that this is really going to be the nth root, that's how we say it, of x, or we write it as the nth root of x. So whatever the denominator of our fractional exponent is, that's going to be the index. So for example, if we have 27 to the 1/3 power, what can we write that as? Well, that's going to be the third root of 27, which we're looking for something 3 times. So this is 3 times 9, that's 3 times 3. So you can see it right there that we have 3 3s. So this is going to get to come out as 3. What about something a little bit more complicated? So for example, if we have something like 4 to the 3/2 power, this is really saying that we want to do a cube and a square root, and you can really do it in any order. So what it means is you could write the square root of 4, so that's for the bottom part. Really, you could write a 2 there, but we don't normally do that. And then we're saying take it to the 3rd power. So this would simplify to be the square root of 4 is 2, 2 to the 3rd equals 8. So the reason why that works is if we rewrite that fractional exponent to be more familiar, which was the 1/2, we already know that means square root, and then to the 3rd. The reason why that works is because our exponent rule says you have a power raised to a power, right? We have a to the m to the n power. This is a to the m n. with some whole numbers. Remember, if we have like 2 to the third squared, this means 2 to the third times 2 to the third, but really that means we have 3 2's here and 3 2's here, so altogether we have 6. So we've already used that before. Just by the meaning of exponents, we know that. We could have also written it as 4 to the third and then taken that to the 1/2, because that would get us the same product when we multiply our exponents. We would still get that 3/2. And now this one, it will look slightly different because it's asking us to actually do the cubing first. So we could rewrite this as 4 times 4 times 4, but that's going to be 64, and then take that to the 1/2 power, which is the square root of 64, which equals 8. So we're getting the same answer. So whether you do basically, if we go back to the original example here, 3 is really the power, and the 2 is going to be our root or our index. In general, we can write that if you have something like a to the m over n, this means that you can either see it as a to the m to the 1 over n, where again this is going to be our index, so that's taking that second and doing the power first. Or you can take it as a to the 1 over n, so do the index, the root first, and then take it to the power. So I normally like to work on this last way because then you're starting to have smaller numbers. So for example, if I'm looking at something like, let's try one more example here, 27 to the 4/3 power, if I use this first kind of definition of that, it would say we'll take 27 to the 4th power, then take that to the 1/3. So in other words, 27 to the 4th power, then do the cube root. Well, 27 to the 4th power, you can punch down your calculator, it'll be the 3rd root of 531,441, and the 3rd root of that ends up being, I'll save you some time, 81. But what's a little bit easier is if you take it as 27 to the 1/3, actually we don't need the parentheses, we're just going to take 27 to the 1/3, and then take that to the 4th power. So that would be looking at the 3rd root of 27, then taking that to the 4th power. So the 3rd root of 27, well, 27 will be 9 times 3, and 9 is 3 times 3, so we get to pull a 3 out. So it'll be 3 to the 4th, but 3 to the 4th is 81. But that was kind of nicer numbers to deal with than the crazier number up above. But both of them work, and that's because it satisfies all of the exponent rules. And so all of this was really necessary when we were looking at our basic function, f of x equals 2 to the x power, because we said our domain for this guy would be -infinity to infinity. For our table, we would only plug in a few whole number values, but now that you can see what those fractions mean, we could kind of work a little bit differently, or at least understand why we say that the domain is all real numbers, because when we make our graph, we put the number 1 with 2, 0 with 1, and the -1 with 1/2, and we connect them. But really that's knowing that we have exponents that are not always whole numbers. They can be rational numbers and so on.